Today we're looking at how rammed earth structures are engineered. This comes from material in the book The Memory of Rock, Understanding Rammed Earth by Gokul Salvadi. We're going to focus on the physics that allow this material to support some really significant buildings.
So let's start with a specific example. In Islamabad, Pakistan, there's a communications tower that's made of rammed earth. It's 100 feet tall.
And the walls that hold this tower up are 3 feet thick. As of today, it's actually the tallest, modern, load-bearing, rammed earth structure anywhere in the world.
Now the tower's location presents a real challenge. You see, it wasn't built in some perfectly controlled, stable environment. It's in a seismic zone, a place that's subject to earthquakes.
So all of this raises a pretty fundamental question. You've got the material, earth, and you've got the conditions, a seismic zone. How does a structure of this scale actually stay standing?
Well, the answer really begins with understanding the core structural identity of the material itself, and it all comes down to the nature of compression.
So, what is compression? It's simply a force that pushes inward. In a rammed earth wall, the weight of everything above it, the roof, other floors, even its own mass, is constantly squeezing the particles of earth tighter together. The same force used to compact the wall when it's built is the very force that gives it strength.
To put a number on it, unstabilized rammed earth typically has a compressive strength of around 3 megapascals, or MPa. Now that can vary, of course, but it's a useful baseline to keep in mind.
And what does 3 megapascals actually mean in practice? It means that even your most basic, unstabilized rammed earth is more than 10 times stronger than what's required to hold up a standard 2-story house. There's a really significant inherent capacity there.
Now, the opposite of compression is tension. This is a force that pulls material apart. And this right here is rammed earth's primary structural weakness.
You can see the comparison here. Under compression, the clay particles in the earth are pushed together and their bonds hold firm. This is the material's natural state. But under tension, those same particles get pulled apart, and those clay bonds release. The material just doesn't handle that kind of force well on its own. It's quite similar to concrete, actually, which also has poor tensile strength and needs steel rebar for reinforcement.
Okay, so if we know the material's properties, strong in compression, weak in tension, how do you actually engineer a building with it? Well, it all comes down to managing how force, or load, moves through the wall. This is what we call the load path.
The load path is basically the journey that weight takes. It starts at the very top of the structure, travels down through the walls, particle by particle, layer by layer, until it finally reaches the foundation safely. The crucial point here is that this path must be continuous, uninterrupted.
And that brings us to the primary challenge in any load-bearing wall system, not just rammed earth. Openings for things like doors and windows. They break this continuous path. The load that was traveling straight down suddenly hits a void.
The solution is something called a lintel. It's a horizontal beam. It can be made of wood, steel, or concrete, and it's placed right over an opening. What it does is catch the load from above and redirects it sideways, around the opening, and then back down into the wall sections on either side. It essentially preserves the load path down to the foundation.
Now, design can handle most of the compressive loads, but in certain situations, tension becomes unavoidable, and that's where reinforcement comes in. In seismic zones, for instance, where the ground itself is moving, or in very tall structures, or when you need to span very large openings, steel rebar is often embedded right inside the rammed earth. It's there to handle the tensile forces that the earth itself just can't.
So this understanding builds from these individual components up to the entire structure. The goal is to design the walls so that they work together as a single, unified system. A key design element here is wall thickness. And it isn't just about one thing. A thick wall provides the necessary structural capacity for bearing weight, sure, but it also offers excellent thermal performance by slowing down heat transfer. And it ensures stability against something called buckling, which is when a tall, slender wall might bow under its own weight. These 3 requirements often point to a very similar dimension.
This really illustrates that system-level thinking. At the very top of all the walls, a ring beam is installed. It's a continuous beam that runs around the whole perimeter, and it literally ties all the individual walls together. This transforms them from being just separate elements into one rigid, unified box. During an earthquake, this is absolutely critical. It forces the whole building to move as one unit, distributing the forces and preventing the corners from pulling apart.
So that tower in Islamabad, it doesn't stand because of some modern trick. It stands because of a deep understanding of these principles, managing compression, engineering the load path, and unifying the structure. The engineering allows the material to behave exactly as it naturally wants to. The wall stands because the rock remembers how to be under pressure.